Thank you all for coming. I like to first, of course, start by thanking the RGC, who supported this with the theme-based. UST also, in part, of course, supported. So thank you, Nancy, Hong, and Wei, who's not here, and everybody else. All right. So what are we really doing? I need to give you some numbers to put things in a context. Why did we start this research? And some of you may not be aware of the numbers. The numbers are worldwide. We lose about 126 billion cubic meter of water each year from water supply systems. To put that in a context, if we save that water, that's enough to run 300 cities like Hong Kong. So whatever we consume in Hong Kong per year, we waste 300 times that worldwide. So it's and every time you lose water, you lose energy because it needs energy to treat it, energy to pump it, energy to bring it all the way from the East River down to here, and that's all. Now, to bring it more to home, and I think because we're gonna be talking about the Guangzhou, but we also have the UST campus. And in the UST campus, just from one pipe, which is near Tower A, it's now actually out of commission, the pipe, because it's leaking, and it's leaking 3 liters per second. Again, what is that? In one pipe in UST, 3 liters per second, that's in 10 days. If we run it in 10 days, that's equivalent to one swimming pool. Okay? One Olympic-sized swimming pool is actually, and it was running for a few years. So we were wasting about one swimming pool every 10 days of fresh water in one pipe. And so the idea is there is really no technology worldwide when we started to actually deal with these issues. So we think we have great potential of getting there. So what I would do today is show you essentially what it requires to run this technology and how it works in a lab setting. And then I'll share with you what do we need to do in the Guangzhou campus if we want to emulate the success that you see in the lab. Okay, so that's, and through that, because I know there are people who are directly involved, we will show you what are the equipment that we might need there to be installed earlier on, or what are the things that, so here is, in this small lab, we are actually able to fit this pipeline, and to make it more realistic, we actually had to coil it. And in coiling it, we have about 150 meters of length. So this pipe here is actually, we're coiling 150 meters, which is about a 1.5 football pitch. Now, this is the main tank that supplies it over there. And the water is actually flowing as it would be in practice. So it flows through here to the outside loop, comes back to then the inside loop and so on, and then it terminates back. So we are doing here a closed circuit because of water saving. We don't want to throw away that water, right? For environment. We will show you, actually, I have, if you don't mind, I'll finish with this. And I'm going to show you, which is probably, none of you know, we have a lab outside, much bigger than this, in Hong Kong, down in Beacon Hill. So I'll show you that, and the pipe is about this size. You will see that, the scale. So we have a video of that, so we don't have to go with video. So this is what it requires. So I'm not going to go through the physics. If any of you later can ask us about the math and physics, but here is what are we going to do? So we'll have the water flowing, and then at this point, we're going to generate a signal. This is, medical speaking, is like doing the echo. So the doctor will send the wave, receive the echoes. So we have to send the wave. And we have two ways of sending the waves. One is mechanical, by operating mechanical device. Here we use a valve. So we have a valve here. We're going to close that valve. When we close the valve, it sends actually signal. These signals move at about 1 kilometer per second. So when we do the testing, you'll see the test finishes in about 20 seconds. So we are doing the health monitoring of this 140-meter pipe in about 30 seconds. And we get back the data, and then we analyze and we look at the images, essentially. So that's, so Maybe you could walk there and show us the valve. So this is in the map, but they will show you the little valve that we will close a bit later, right? So there we're going to send, but like when medical, you send, you need to receive the echo, right? You need to receive the signal. So we have these pressure transducers, and we need to connect this to the pipe. So already, since we are talking about Guangzhou, we will need a place to send waves, because believe it or not, when we go now and apply this in Hong Kong, there is no place to send waves. The pipes are already underground. You have nowhere to access them. We have no place to attach this. So already accessibility is a key. Even on our campus, I'll show you what we try to do on our campus, but we cannot get into it. All right? There is no place to get into it to do. So it's like having a patient, but that patient is, the doctor cannot access, cannot get to. Right? Yeah, all wrapped up, cannot access, cannot do much to it. Right? So we have to first do that. So maybe you can show us the transducer, and best it's connected right to the pipe. Like when because here, what these transducers are doing, what the doctor does when they measure your blood pressure. Okay, they do it there, you know, and that's what we need to do. So in most places, we don't have that contact directly with the pipe because civil engineers are great at burying things, right? And is he losing the signal? Anyway, it will be connected right on, and therefore access for that to generate and access to receive is a key to this, right? And accessibility points, therefore, are key to any smart system. Believe it or not, most cities, we cannot do this because there is nowhere to access any of the pipes. Somebody built it that way, the Romans did, and we copied that. We forgot that there will be technology that would come in, and we need to bring them in. So now let's see, I think that's all I have to say now. So what we're going to see now, the test running. We're going to now generate the signal. So we're going to close that valve, and automatically the system will collect the signal, right? And we automated now our signal processing techniques that will estimate the leak. By the way, the leak is here, is now 98 meters away from where we are. So there is a leak there, and later on you can see it. It's actually over in that location. We simulated. We put a hole in the pipe, and we're simulating a real leak. So you can see it later. And now we also, so why don't you do the echo, right? Do the test. Yeah. Okay, he needs, what are you?
We need to share with the Zoom.
Okay, share. Well, now actually we're working with outside consultant. We're trying to automate even that. We could send these valves, we could automate them with GPS, and we close them from our campus here. We could send the signal, get the data automatically. So we're actually building. We're going to start first by testing it in UST, and as part of the project that Hong and those guys thankfully supported us. So we're already testing that here to automate everything, right? So we don't need, we're going to get the human out of the chain, right? So this is the background pressure now. This is, and now you will see a wave once they close. You will see that's the pressure signal. This is the background because it's turbulent flow. So you see quite a bit of fluctuation. Okay, so you see that's the waves, and those are traveling at kilometers per second, already enough. So now that's it. That's the echo. It's not really that fast. And now you're gonna go in. Okay, he wants to wait for the signal to damp out completely, and we will. We used to take these data to the lab, but now it's all automated. We have 3 signal processing techniques that we've been testing to see consistency between them. So if all goes well, we should be close to 98 meters, right?
How long
yeah, it's really for these what we call low frequency. Mechanical device, you can't close them as fast. She tried her best. Juliana tried to close as fast as possible, but it's going to be in the order of a couple of hertz. And with that, waves can go very, very far. So it could be kilometers. Well, we tested this in Italy for up to 10 kilometers, and it could go.
Still strong enough to
Yes, right, exactly. But I'll discuss with you in about 10 minutes the high frequency, which brings us big resolution, but then the signal becomes more limited. Right? So it's
During these the test,
yeah.
do you have to shut down the?
No, the system was running.
But
Yeah.
then with the water flow or whatever utilization,
We don't. If we're going to do it mechanical, usually if we are designing this, we will have a side discharge. So here is your main pipe.
like this, like
Yeah, yeah. You see with it? We'll leave the flow untouched, and you'll have a side discharge. You get a bit of water coming out, and then you close the side discharge. You don't close the main pipe, right? So the operation can continue. This is now the signal will actually detect it, because when we send the wave, you're going to reflect off the leak.
water leak is the signal will be probably different from the mechanical on and off signal because you
No, no.
mentioned that it's a low frequency.
But when you send that signal from here, when it finds a leak, the wave will reflect back. That is, part of the wave will come back because it's finding discontinuity in the pipe. It's essentially, you're sending pressure. When it reaches the leak, part of the pressure will be relieved, right? The water will spurt out, and that sends back the waves. Part of the wave will transmit, the other part comes back to us.
how
What?
sensitive would that be? Just effect without really too much.
Signal to noise. So we really need, it's an SNR problem. So, and that's part of what we need to measure again in the background, is if we put these sensors measuring day in, day out, we get a good idea of what is the background. And we need to send our signal stronger than that. We don't want to send the signal very strong because we'll break the pipes or fatigue with time. So we are optimizing there. But we've been dealing with this. So pressure of about 5 to 10 meters is what we usually send, equivalent height.
This is
Right.
working on the water supply, right? But
Yes.
How about if it is like a slurry? Would it be applicable as well?
We are actually testing now with drain. We got a project with Drainage Service Department to test with the sewage.
Yeah.
The difficulty in sewage is the material properties. So that means the wave speed. In water, we know the wave speed. It's about 1,000 meters per second. For sewage, a little bit of gas can change the wave speed from 1,000 to 200. Less than 1% of air in there, and you can get all gases, right, released from the
So
chemicals.
turbidity
Yeah.
actually will affect.
Yeah, it will affect the wave speed, but that we are measuring now to see how that goes. So do you have the? Oh, so those are the estimate. So one of
Close enough.
yeah, and wow, okay, that's too close. In fact, too close. Usually, what you expect here is within 5 to 8 meters, right? And the reason is because of the low frequency. With the low frequency, there is a limited resolution, which is half the wavelength, right? And given our so when we do these, it means we are super lucky. So we tested this morning, and I think what is it? It was 93, 98, and 102, the three techniques, right?
But you can locate location of the leak, but you don't know how thick a leak is.
Well, again, we estimate it, but we are usually off. And the reason, because our physics of modeling how much, because of the turbulence, we don't really get that well yet, and we're still working on that. But when we talk to the water supply, they say they don't care. Just tell me where the leak is. I don't care how big it is. I want to close it. I want to deal with it, right? Yeah. Yeah. Again, as we said, it's an SNR problem. Give me a system with no noise, we can give you a very good reflection from it.
But normally, you have unless you have a respective the signal is really low, and the signal to noise ratio is low. And in that case, how are you going to handle it?
No, I mean, we cannot really beat the physics. If there is no noise, then we can go down quite low. If there is, then we have to send the stronger signal. I mean, how you get it is you need to by by these mechanical. So here we're sending 10 meters. We can send 50 meters if we want. We can send 100 meters. And that's the case. If you really want to send a big one, you might need to close the whole pipe to send a bigger pressure. But we don't want to do that. We don't want to destroy the system out. But maybe if you don't mind, let's go quickly to our, because it's interesting to see our other, yeah, keep going.
In the case you have a really complex distribution network.
Yes.
Not the pipe we need. With that, the positioning be a problem.
As
A lot of branches.
again, branches are only a problem in a sense it reduces the signal. So if I'm sending, because when the wave reaches a branch, its amplitude gets divided. Part of the wave goes here. So I send a wave of this much, it becomes smaller, right? So if I really want to image that, I need to send a bigger wave to start with. But where these things become more of a problem in practice is cities don't know where their branches are. Cities cannot tell us how many pipes they have. And we will discuss a little bit of that. And that's another key to our system here. Because maybe as he's getting this ready, one of the problems we faced when we tested here in UST is they don't know where the pipe is. We don't know. In fact, they had, I think, 2 consultants before or 3. This pipeline has been leaking for more than 10 years. And now it's closed, it's out of commission, waiting either we might have to throw it away or hopefully we try to find it. So we are playing with it, but the data we have about it because the contractor who built it, again, who cares? It's a pipe there. So what happened is 6 years ago, I think the university paid a consultant. The consultant, because I guess he asked, where is the pipe? And we gave them the maps. So the consultant predicted the leak to be between tower A and B, right? So they went there to dig to find the leak. They could not find the pipe. They didn't, it's not about finding the leak. The pipe was not there. And we cannot image a system that we don't even know where it is, right? So this is the other message that I tell water supplies department, and I'm telling here at the Guangzhou campus, keep good data, because all cities don't, right? There is no city that does this. Most cities, they don't know about 70% of their pipes. The other example is when we were building the IAS building and the business school, if some of you may recall, the construction stopped for a couple of months because they found a pipe under that road and they called water supplies. Water supply says, I don't think it's ours, but whose it is? Can we cut it? No. What do we do with it? In fact, we had to go with FMO and test it to tell them it is a pipe, but there is nothing in it, right? So it took a couple of months of delay. So there are pipes that there is no record of them, but they looked in good, they were actually in good condition, all right? Anyway, so we cannot. So really accessibility is a key, and that's really my key message if we're gonna do this, accessibility to new technology, not just ours, by others in the future. You need to be able to test them and to know where your system is. If we don't know any of those, then forget it. Doesn't matter. So being smart is already knowing where you put. Okay, so here's, you talked about scale, right? You asked about scale, and this is interesting because I don't think even Hong knows. This is in Beacon Hill. This is actually given to us by water supply. This is a tank, and our pipeline goes, you will see it. Yeah. You did? Okay. So we are getting the water from another reservoir on the top of the hill in Beacon Hill. Right? So this is our pipe here. This is actually the connection from water supply. So we are connecting directly to their system to make it more realistic. Okay. And this is about the scale. You can see now this pipe. So we're actually walking you through it. All right. So you can see it's actually much more massive than this one. Then it has all of these turns. So on total, we have 250 meters length, okay? With branches, because you asked about branches. Okay, so it keeps some. Yes. Well, we probe it. A leak is there. The leak is there, steady or unsteady, right? But when we probe it, we're sending waves. Right? So there is really, when there is a leak, there is a leak. It's not a matter of it's there, it's steady, it's there all the time. But what we do is instead of trying to say, okay, there is this steady flow, we actually send this wave to reflect off it. It becomes a reflector. Yeah. Sorry? Because otherwise I'll tell you where the location is, and like what they don't find the pipe at all, right? so that's where knowing the system, because when I get it here, it tells me time. Physics tells me time. I need to convert time to distance. So distance, I multiply by wave speed, so knowing the properties, and that's what the sewage is. But distance from where? I need to tell you it's distance from here, right? If you give me the wrong path, then I'm going to send you to the wrong place. So now maybe you could show us what we predicted with that pipe. With this is the one in Beacon Hill, so it's a different system that we send. Okay, so here again, the water is coming out, and we're going to do the same operation. Close this valve that generate the signal. This is the waveform we develop, and that's the signal we measure. We put it again through, and this is the real leak. The peak of the blue is our estimated. This is the error margin. That's our confidence interval, if you want to think of it that way. And you see it's of the order of 10 meters or so. Why? Again, because we're limited with resolution. We're limited frequency. And with the valves, we can only do a few hertz. So the way we're thinking about it is we want to do this low frequency because, as you asked earlier, it can have a big range. So that will give us an idea that there is a problem. But water supplies tells us that accuracy is key. Because, for example, we are also testing in Yulong, and we know that there is a leak in Yulong, but it's very close to a highway. So in fact, the prediction is under the highway. So they're saying, you'd better be right. because the police is going to be, we have to inform the police. They have to actually block all of that, disrupt the traffic. They're going to have to scrape the whole road, and we want to make sure it's there. So accuracy is key. And how do we increase accuracy is we need to probe it with higher frequency. And that's, so now here we send a few hertz. George will just now show you some results. We are not going to do the test. We'll just show you an output when we run things at the kilohertz level. And his test, I think, is about 35 kilohertz that we did it, and you get it down to a few centimeters. But again, now with these, maybe you can show the transducer. We cannot do it by valves anymore. We actually have to do the transducers, the ones that doctors use. We have to insert these into the pipes inside the water. And for those, there is nowhere in any system in the world now where they actually envisioned that and allowed for us to insert it. So it's a technology waiting to be employed. But when we're building a new place, we can. Now, I guess our image, it will be the living lab, collect big data, allow us to access, build it now, and it could be really a place to show all the cities first around us in mainland China, because there is a huge interest in this. They have leaks much more than Hong Kong, right? And that's the way to show it. We can show it in a lab, but only if we can show it in a real living lab, then it could really take off. So it could really play both. And that's, I guess, what we want from this system. We cannot do it on campus here because we have bad maps, right? It's mainly there is mainly SCADA system, and these SCADA system are really measuring things at every few minutes, 5 minutes. So it's not a wave based. It's measured on the basis of steady state, right? And looking essentially at the change in flow. But for that, you need a lot of understanding and good measurement of dissipation, because and we don't have that. They can have that in the oil business, right? They measure that. They measure from the first day. They keep good records. They keep good data, and they sample for water supply. Lots of them have not been sampled for 30, 40 years. So our idea is to do it really on wave basis. First, you do it as a shot. It's very quickly. You get your image, and but we are hoping actually to extend what we do to those systems, because we talk to them and they say, if you guys can make this to work, they would love to have it. But this is what they do now. The reason they have less leaks is because oil is expensive. Yeah. So when they build them initially, they build them to much higher specs. All right, that's so maybe George, you can show the transducers. Something that needs to be thought now, if that's what we want, then a provision to be able to
some micro robot.
Sorry.
So it's
Well, that is actually an MIT professor working in our group. He's with us in our project. He does robots for pipelines. Right? So, so we have that possibility.
And you also need to surface them too, right? If you break in the future,
Sorry?
You need to surface them, right? If you are putting inside, then it's actually broken in the future.
Well, the robots will be very useful, but in the first portion, the first 5 years of our project, they said put away the robot. RGC told us focus first. First focus on being able to detect and then tell you about robots.
What you can do if you have a magnet that could move along the pipe.
So
then
let me just explain, because well,
This is our robot now.
but you have to insert it manually. So that's why I need enough space here to put the transistor with the base that we put a magnet on inside the pipe, and then the other magnet that's on the surface of the pipe is attached like that. So you can actually mount it, and you can control its longitudinal position. You can slide it in and out, and you control its both radial position, that's mounted at the center, and its longitudinal position. So as I said, we can send high frequency signals. So we tried to identify some blockages and leaks as well. And let me show you the results.
So really what you're gaining is the precision, right? The confidence.
The idea is the same. We're sending a wave, and the wave meets a defect, that's a blockage or a leak, and is reflected and scattered. And we receive back that identification of that defect, and then we can calculate the distance where the reflection came from.
Why do you need the wire? Can you use the wireless mic?
Sorry?
You use wireless mic, the sensor, but why do you need the wire? Could it be wireless?
We're actually again doing this wireless now, but we have to synchronize. We're working on the synchronization, so we can do it all. But now,
and you have to keep in mind that it's high rate data acquisition, so it's 1 megabit data rate acquisition. So we need to have good resolution of signal. So, well, in this case, since we're in a lab, wires is working fine for us.
But
in practice,
but in the system in USD, we're looking at the.
Of course.
But the pressure would drag this thing forward, right?
Sorry?
How do you anchor this sensor? You have pressure inside the pipe. You would drag this thing forward.
No, because it's pretty much uniform. Right? You don't really have a lots of gradient. Right? It's what matters is the gradient of the
But there'd be
pressure.
water flowing inside.
Yeah, I know, but you just have that's the pressure gradient that creates is very low. So the drag force it creates is small.
You make it smooth and streamlined.
So the drag force is not
the magnet to hold it in place.
Yeah. And this is for the testing, but of course, again, if we do it in the Guangzhou campus, we will not do it by magnet, right? We have to put it fixed places where we put it when we need to.
it's not the ideal mounting technique. It's just gives you an idea of what we're looking for. So maybe actually mount those transducers inside the pipe.
Maybe quickly you can show results here.
Sure. So this was the idea, as I showed you already. We put the source and the receiver inside the pipe, and we have a defect located at a distance from that point. And we're sending a signal. And that meets the blockage And once it meets the blockage, you get part of it reflected and part of it transmitted. So the receiver will receive, this is the reflection, this is actually what we send, and this is what we receive. And you see that because it's the receiving transducer works at the same time as the source, you first get what you send, and then after some time, you get back the reflection, right? So once you get the reflection and you isolate that reflection and run it through our model that we have, we can actually identify the location of the blockages. And we tried different blockages with different materials. And you see that, well, I measured, when I have to insert manually the blockage inside the pipe, the same way I do that with the transducers. And I measured this about 1.2 meters with a ruler, with a tape. But from the model, you see I can get results that are in the scale of centimeters. I can identify the location of those.
Plus or minus.
Plus or minus the half the wavelength. Yeah. In this case, the wavelength is about 5 centimeters. So plus or minus, the error is 5 centimeters rather than 10 meters. That was the case for the previous setup.
So it's more precise.
Yes, it's precise. So the idea is to combine those two techniques together. So first, we would like to use the low frequency waves to more or less, with accuracy of 10 meters, identify where the defect is, roughly at this, yes. And then,
sorry, in the interest of time, for you, for us, we are here all day. But can I just show you one more slide because it's about the UST, what we do.
Sure.
We see something frequently. And then
So it's to combine both.
There are more questions.
Yes, exactly.
Ask us.
But of course, you need the infrastructure for that.
Yeah.
You need to have the transmission inside the pipe already. So.
So interesting.
So this is actually the system or the pipeline UST that we are trying to
Play with. This is tower A. Tower B, and this is where the unibar is. Okay. So all of you know the unibar, you may not know the rest. Okay. And this there is a pumping station here. The trouble, what I was mentioning, is we don't really know much about the details of this pipeline. We don't know the configuration. It's we know what the maps are, but the maps are obviously wrong, as was found. And we also have no access. The only place we can access is basically here or at Tower A or there, but it's also on the side. And you have a lot of other connection. We cannot really get the wave to be directly sent. So these are already the trouble we have. You can see this is actually simpler, and topology simpler than a coiled system like this. But the reason we're having, we have now guesses, but the guesses are contingent on what is known to us. So the reason we are unable to actually find, and by the way, this leak is very large compared to what we can test here. So give me the good information, and I'll give you what that is, because it's a simple system. So the trouble we have with it, it's unknown, and that's what we don't want to have. And I remember when we first started doing this, when I talked to many people in the university, I said, no, we know everything about our system. We are University of Science and Technology. We're new. We don't. It's not our fault. It's just that's how the tradition. Tradition is we have enough. You know, what else do you want to know? So really, if there is the interest, we will be very happy, of course, to work and say what is required, right? More to do this. So at this stage is put it in the design. The Hong Kong, you may know, it has a part that is now done as a smart city, just before Chong Hong, right? Yeah. And Anderson Road.
Anderson Road.
So it's going to be an area, and in fact, we are acting as their advisor in terms of these, and we're giving them exactly the same message. You know, how do we make it smart? Well, keep some good data and make it accessible. So they're trying to work through that. But I think in our campus we can perhaps, because that's going to be ready by 2022.
Yeah.
We can already do it and show them, and because they want to use that as an example to then hopefully propagate these ideas, at least in Hong Kong. All right. So now I know you have to go. You've been very kind.
I know that the plan for this is very common, so accessibility should have the issue.
Sorry.
In the new campus, one is potentially the problem is that transducer inside the text. Do you have any spec or recommendations?
Well, I know every pipeline will have a fire hydrant, right? And the way the fire hydrant we have them now is just basically a pipe and to connect to fire. But there is a Swiss technology that already thought of these things. They now sell fire hydrant with the idea, the ability that you could have attachment where you could put sensors and technology in it. So at least we could look at that, right? So wherever you have a fire hydrant, you could have an access point to a lot of these. You could put them in and take them out. And there is a Swiss technology to that effect. How much has it been tested? At least I know in Switzerland they are testing it, right? But again, they are testing not from this aspect. In their case, can we design a platform that will allow for technologies to go into the pipe? So there is such a thing. Okay? So the easiest initially would be through a fire hydrant, possibly. Right?
Yeah. And we can upgrade. We don't need to go to one.
Yeah, and you don't need to go to one.
You don't want to go?
No, we can upgrade from here.
Thanks a lot. Thanks a lot. Thank you. And what we'll do is stay here for another 10 minutes in case the outside people have any questions for us. Yeah. Okay.
Thank you so much.
Sure. Thanks a lot. Take care. Yeah. Thank you.
Come here to see it.
Yeah.
If you give a presentation there.
It really not. Yeah, and really that's my thoughts because you need to see the equipment, you need to see how it's all. So hopefully it's much more clear.
Yeah.
Right. And let's see. It's not easy, but that's what we should target.
Very
Yeah,
good.
sure. No, we actually that's multi-dimensional. So when we go high frequency, we're diameter to wavelength, right? Yeah. Helmholtz number. That's it. All right. See you. Bye. Bye. Take care. Bye. Thank you. Thank you.